students. So, last time we had looked into the construction of horseshoe attractor, and today what we are going to see is what is the dynamics of the horseshoe map on the horseshoe attractor. So, last time we had seen this construction, the horseshoe attractor, and we have the horseshoe map F acting on it. Now, this resulted into coming up with another, the space of all sequences of zeros and ones, and we will now look into that space once again. So, we have this space sigma and if you look into this, this is anyway this is a topological space given the product topology, but we can also think of giving a metric to this particular space. So, let us look into two sequences here. So, my sequence S happens to be say S minus k, S minus 1, S0, S1, Sk and so on, and S bar happens to be the sequence S bar minus k, S bar minus 1, S bar 0, S bar 1, S bar k and so on. So, we have two such sequences and we can define a function d on sigma cross sigma. So, we define this particular metric, I should say S S bar, which happens to be summation over I from minus infinity to infinity. I look into delta I upon 2 to the power mod I, where my delta I is 0 if my Si is same as Si bar, and it is equal to 1 if my Si is not equal to Si bar. So, now if we look into this D, this D clearly defines a metric on this particular space sigma, and the topology that D gives is same as the product topology which we are considering on this space. So, we can say that this particular sigma is a metric space. Again, this is a compact metric space, since we know that 0 1 is compact. So, our sigma happens to be a compact metric space under this particular metric D, and now we shall try to look into the shift map that we had seen last time. So, what is this shift map? So, we can think of sigma from this capital sigma to sigma, the shift map defined as is given as so, you are shifting all the symbols one places to the right, or I can say that sigma of S right at I will be actually equal to what is S at I plus 1. So, this is the shift map defined on sigma, and for this particular shift map now it is very easy to see that this will be a continuous mapping. So, sigma is a continuous mapping on your space of sequences, and we shall now look into the dynamics of this system sigma sigma. What is the dynamics that you can observe over here? So, if we try to analyze this part, right now, since we know that very well that our sigma is just by infinite sequences comprising of 0 and 1, we can think of many sequences arising from here, and one of the sequence that you can observe over here is this sequence constant 0, and we call it, we just denote it as 0 bar. So, 0 bar is the sequence of all constant zeros. Similarly, you will have 1 bar which is the sequence of all constant ones. So, you have all constant ones. Now, I can think of a sequence where I am alternating my zeros and ones. So, I have a 0 and 1, I have a 0 and 1, I have a 0 and 1, I am just alternating between the sequence 0 and 1, and I can denote this as 0 1 bar. And similarly, I can have a sequence where I am alternating 1 and 0, and I can call it a 1 0 bar, right. These are alternating sequences. And now what we find over here is that my 0 bar remains fixed under sigma, my 1 bar remains fixed under sigma. If I take the image of 0 1 bar, what I get here is 1 0 bar, and if I take the image of 1 0 bar under sigma, I get a 0 1 bar. So, the essential part here is that if I am looking into the sequence 0 1 bar or 1 0 bar, we find that under sigma square, right, 0 1 bar remains as it is and 1 0 bar also remains as it is. We do have periodic points. So, sigma does have fixed point at 0 and 1, 0 bar and 1 bar are fixed points, and then these are period 2 points. Similarly, you can look into this part that if I am taking sigma cube of say 0 0 1 bar, right, which is again like the sequence 0 0 1 repeating itself, we find that this is going to be equal to 0 0 1 bar. Similarly, if you look into sigma cube of 1 0 1 bar, right, that also remains as 1 0 1 bar. So, you do have periodic points of period 3, and we know that there are total 8 possibilities, right, of such sequences, such triplets, and so you can say that there will be something like 8 periodic points, right, or 8 fixed point or 8 points sigma cube equal to x, 8 fixed points of sigma cube x equal to x, right. Now, similarly, you can go forward and for any sequence of length k which is repeating itself. So, supposing I have a sequence of length k repeating itself, then I find that sigma k of that particular sequence of length k repeating itself, right. So, maybe I am looking into in terms of S1 up to Sk, right. I find that this is nothing but this is my S1 Sk bar, where my SI's belong to 0 1. So, we find that this constitutes, right, this will give me periodic points of period k, right, and hence there are periodic points of period k for all k in n, right. So, what we can conclude from here is, if we pass on like this, that sigma has periodic points of all periods k in n. Now, the interesting part comes up here is that okay fine, we do have periodic points, but can we have non-periodic points? So, let us again go back to say our interval 0 1. So, consider this interval 0 1 and for x in 0 1, consider the binary expansion Now, if I look into the binary expansion of x, any x in 0 1, then again what we get is a sequence of zeros and ones, and we all know that the irrationals, right, the irrationals in 0 1 they correspond to the non-repeating the non-repeating sequences of zeros and ones, right, normally correspond to the irrationals in 0 1, and we know that there are uncountably many irrationals. Now, let us go back to our sequence space, right. In our sequence space we have many sequences of this particular form, and I can always associate, just forget what was the past part, right, and I can associate this sequence to just looking into its present and its future. So, that means I am just looking into the one half of the sequence, right, Sk and so on, and every sequence can be associated to such a sequence. Now, again look into the irrationals in 0 1, right. The irrationals in 0 1 are giving us non-repeating sequence of zeros and ones, nothing can come back to itself, and if I try to apply shift map over here, right. So, if I look into the non-repeating sequences of zeros and ones, and if I say that my S0, S1, Sk etc., this was a sequence which is non-repeating sequence of zeros and ones, right, then basically that corresponds to a sequence, that corresponds to some kind of sequence in my space sigma which is non-repeating or which cannot be periodic. So, the non-periodic points in our space sigma correspond to, basically I can say that it can be corresponded to the non-repeating sequences of zeros and ones, and hence what we can conclude is that there are uncountably many non-periodic points in sigma, or I should say the system sigma. So, this system is very special because it has periodic points of all periods as well as it has uncountably many non-periodic points. What other kinds of points can we look into here? So, let us try to again take up all the sequences, and now we try to give some kind of order to the sequences. So, I am trying to look into say all sequences here, say sequences of length k. So, I want to say that Sk, right, is basically the set of sequences of length k. And now we want to give some kind of a order to all finite sequences. So, because these are finite sequences now, so we want to give some kind of order to the finite sequences. So, we say that let say I want to say Sk and S bar k prime be finite sequences. What I want to mean here is that Sk belongs to Sk for some k, and Sk prime k prime bar belongs to S of k prime bar, right, for some k prime. Now, what we are interested in looking into is some kind of an order. So, we define an order on these sequences. So, we say that Sk is less than Sk prime, S bar k prime is less than Sk bar prime First thing is k is less than k prime, but if k is equal to k prime, right, then what happens, and if k is equal to k prime, then we know that this will consist of n sequences. This will consist of, say, my Sk happens to be of the form, right, S1, S2, right, Sk, and my S bar k prime happens to be of the form, say, S bar 1, S bar 2, right, S bar k prime. And now since k and k prime are same, that means these two are the same, right. Then we say that Sk is less than Sk prime if I am looking into Si of Si, right, is less than S bar I, right, where I is the first instant where Si is not equal to S bar I. We try to now compare these sequences, say S1 is same as S bar 1, S2 is same as S bar 2, we try to compare this part and then we see what happens at the ith instant. Supposing the first place where they are not equal, right, then if my Si is less than this, then this is less than this factor. So, we have an order on all finite sequences of zeros and ones, and now we will try to use this particular order to formulate something. So, now what I have here is, say I am looking into S1, right, then we know that sequences of length 1, right, there are only two sequences of length 1, one is 0 and one is 1, right. So, I can say that this is S1 and I am writing 1 here to denote that this is length 1, right, and S2, right, this is length 1, right. I just have two sequences here. If I am looking into S2, I know there are 4 sequences here of length 2. So, I am saying that this is S2, I have first, second, third, fourth, right, and it is needless to say this will be my 0, right, this will be my 1, this will turn out to be 0 0, this will turn out to be 0 1, this will turn out to be 1 0 and this is my 1 1. Similarly, I can think of my S3, right, to be equal to S3 1. Now, I know that I will have 8 such sequences. So, S3 8. For length k, I know that there will be 2 to the power k such sequences. So, this will be of the form, we can write this as Sk 2k, Sk1, Sk 2 to the power k, right. We have all these distinct sequences. Now, I want to define another sequence S using these sequences. Define S belonging to sigma S. Now, how do I define my S? So, what I do is I start with the midpoint here, the decimal point here. So, I am having my S1 1 here, S1 2 here, then S2 1 here, S2 2 here, S2 3 here, S2 4 here. Then I should have my next, because I have exhausted all my sequences of length 2, I am now going on to sequences of length 3. So, we have S3 1 here and I have S3 2 here, I have S3 3 here, I have S3 4 here, right. Similarly, S3 5 will be here and S3 6 will be here, S3 7 is here, S3 8 is here. Now we have exhausted all sequences of length 3, right. We now go up to length 4. So, like that we can keep on adding sequences on both the sides of the decimal places, and the sequence that we define in this manner is our sequence S. Now, my claim here is S has a dense orbit in sigma. We try to look into this particular claim, and so we start with any sequence, say S prime. So, I start with the sequence S prime, and my sequence S prime can be written as, say, S minus k prime, right, S minus 1 prime, S naught prime, S1 prime, Sk prime, and so on. So, we have this sequence S prime, and for this particular sequence S prime, we want to say that there is some point in the orbit of S which is close to it. So, we try to look into now under this metric. So, what happens if some other point has to be close to this one? So, supposing now my S double prime, which I am writing it as sequence S minus k double prime, S minus 1 double prime, what is the meaning of saying that d of S prime and S double prime is less than epsilon? So, I can say that given epsilon, some positive epsilon, what is the meaning of saying that d of S prime and S double prime is less than epsilon? So, we again go back to the definition of the metric D, which says that it is basically the summation of, maybe I should say, delta I upon 2 to the power mod I, and what happens in that case? So, for this summation to be arbitrarily small as possible, right, what is needed is that in the middle part, right, somewhere in the middle part, these sequences should have the same value, because only then and then you can make the summation as small as possible. So, if we try to look into this metric, this means that under some, say, there should be some value here such that this middle portion is same as this middle portion. So, maybe there is some n here. So, I can say that this is S minus n prime, S minus n double prime, and I have S n prime and I have S n double prime. So, I should have some such portion, middle portion, which is the same in both the sequences, for this to be made arbitrarily small, right, maybe as small as epsilon. So, we can say that this means that, so this is saying that if I look into this block, middle block, right, so I am looking into S minus n prime, right, up to S n prime, this middle block is same as the block S minus n double prime and S n double prime. So, these two blocks are the same. We want to look into, so now we have started with our S prime. So, we start again with our S prime. So, our S prime was so, this is our S prime, and we wanted to show that this orbit, the orbit of our sequence S, comes very close or maybe comes epsilon close to S prime. Now, so for a given epsilon positive, right, we find that all the sequences which are epsilon close to S prime, right, should agree on the middle block. So, that means that if I am looking into the middle block here, so somewhere in the middle block, right, but maybe let me write here S minus n prime and S n prime, right. So, that means that this all the sequences which agree with S prime on this particular block are epsilon close to this block. And now, when they are epsilon close to this block, right, we are interested in this particular block. Now, if I look into this block, this is a block of length 2n plus 1, and if I look into my sequence S, right, my sequence S is basically consisting of all blocks of all possible lengths. So, that means that this particular block of length 2n plus 1 would be lying at some place, right. We do not know what that place value is, but at some place in S, this particular block is also there existing. So, we find an n. So, basically we can say that there exists an n so that if I am taking sigma S, right, and I am looking into this particular blocks, sigma n of S, and I am looking into this blocks, the block of sigma n of S from minus n to n, right. So, this block will turn out to be nothing but S minus n prime we find an n, maybe the n is positive or negative depend on how we have placed the sequences, but we find that there is some place here where you will find that this block appears, and that is all we needed, right. So, in the epsilon neighborhood of S prime, we find a point from the orbit of S, which means that the orbit of S is dense in sigma. So, all that we can conclude here is that sigma, this particular system, when I am looking into sigma sigma, this also has a dense orbit. So, let us try to summarize this particular system here. So, I can summarize this in form of say a theorem. So, for the system sigma sigma, we have periodic orbits of all periods, right. The next thing what we have observed here is that we have uncountably many non-periodic points, and the third is we have infinitely many points with dense orbit. Now, why do we say infinitely many points with dense orbit? Because if S has a dense orbit, right, sigma S also has a dense orbit. What about sigma inverse S? Okay. We did not discuss this earlier. All we have seen is that sigma is continuous. Is it 1 to 1? Is sigma 1 to 1? Because if you are shifting it by 1, right? The sequence remains the same, that means your original sequence was also the same, right. So, sigma is 1 to 1, sigma is also 1 to, right, because anything you can look into fact, right. So, can I conclude that sigma is a homomorphism? So, my sigma inverse is also continuous, and that is what we are using for the fact is that our block could be on the left hand side of the decimal point also, and when it is in the left hand side of the decimal point, we can always traverse backwards and then we can reach, we have this orbit which is into the neighborhood of S prime, right. So, this sigma is also homeomorphism, and hence if I am looking into if S has a dense orbit, right, sigma S has also a dense orbit and sigma inverse S also has a dense orbit. In fact, sigma square S also has a dense orbit, right. So, you can have infinitely many points which have dense orbit. So, the dynamics of this is very clear. Now, our goal was looking into something more. We will come back to the dynamics of this once again, because this is a very interesting space, but our goal here was to look into the dynamics of the horseshoe attractor. So, let us get back to the horseshoe attractor. So, we were interested in the horseshoe attractor, and we found that any point P in lambda was corresponding by phi to this sequence S. Let us try to look into this part. This point P, right, was the unique point, right, with this vertical line V intersecting with this horizontal line, and this corresponded by phi to this particular sequence, and this is basically a point of sigma. So, we can say that for every P belongs to, we get phi P belongs to sigma. Now, we had also seen this, but it is quite easy to see what happens here is that if my Fp, now I am looking into Fp, my Fp, because sigma is an invariant, this lambda is an invariant set. So, Fp also belongs to lambda, and for Fp belonging to lambda, right, what we get here is correspondingly is phi of Fp. But if we try to look into what is phi of Fp, we have seen this last time, this is nothing but this is my sigma of phi p. Because what is Fp? Now, since we are just trying to take one part to the right, right. So, we get Fp lying in as a point of intersection of a different vertical line and a different horizontal line, and what does that turn out to be, right? That turns out to be nothing but under the summation sigma, I am just moving one point apart, right, because my P happened to be the set of all points such that if you remember that this was like Fip belonging to H of Si, right. So, if we try to look into that, if I am taking Fp, it is nothing but we are just shifting everything to the right, right. So, phi of Fp is same as sigma phi p, and I can simply say that my Fkp belongs to lambda is same as saying it will give correspond to the image which is phi of Fkp, and what is that equal to? Right, belonging to sigma. Now, I want to recall a definition which we have done earlier. So, I am recalling this definition. So, this is the definition of a property called topological conjugacy. So, I am given systems xf and yg, right, and for this systems x and yg, if there exists a homeomorphism h from x to y such that h of f equal to g of h, then the systems xf and yg are conjugate, topologically conjugate, and though we had discussed this earlier, right, I will again try to recall what happens here. What happens when two systems are topologically conjugate? Orbit of one corresponds to the orbit of other, right. So, that means that if my xf has a dense orbit, there will be a dense orbit in yg also. If my yg has a periodic point of certain period, right, my x will also have a periodic point of the same period. So, that means that orbits of both the system, first of all, since there is a homeomorphism, right, each of the points here are identified with one another, right. So, you have the same number of points here. So, every point here is an image of some point here, every point here is also can be considered as an image of point here. So, the points are identified, not only are the points identified, their orbits are also identified. So, that means the dynamics of xf and the dynamics of yg are the same, and that is what we are going to use over here. So, now in our case we have this system, right, say lambda f, and we have another system, right, sigma sigma. We have these two systems, right, and we have this mapping phi which takes every point in sigma lambda to every point in sigma. So, now let us look into this map phi once again. So, phi maps lambda to sigma, and how does it map? We have seen that part also. Now, my claim here is this phi is a homeomorphism. So, phi is a homeomorphism, that means my phi should be continuous, my phi should be 1 1, should be on 2, that is enough, because since both my spaces are compact, that is enough for me to conclude that it is a homeomorphism. So, first of all observe that phi is 1 1. It is injective. Why is it injective? Supposing now I have 2 points p and p prime such that phi p is same as phi p prime, right, and that corresponds to the same sequence . What does that mean? This point p corresponds to this sequence if it is the unique point of intersection between this vertical line, right, which is indexed by this factor, and the horizontal line which is indexed by this factor. This is a unique point of intersection. But if my p prime is also corresponding to this particular sequence, that means p prime is also the unique point of intersection of the vertical line which is corresponding to this factor and the horizontal line which is corresponding to this factor, and that means that p should be equal to p prime. There is no other option, right. So, our next observation here is that phi is onto, that means phi is surjective, and that is always possible, because always any vertical line and any horizontal line will always intersect, and it will always give me some point p in lambda, right. So, this particular phi is always surjective. So, there always exists a p in my lambda such that phi p can be corresponds to this particular sequence, right, which comes up from the intersection of a vertical line and a horizontal line. So, this is always surjective. A little involved part would be to see that this is continuous. So, we want to say that phi is continuous, and in order to see that phi is continuous, all we need to look into what happens if I am saying that there exist points p and p prime, right. So, supposing for p prime belonging to lambda, what is the meaning of saying that the distance between phi p and phi of p prime is less than epsilon. So, let me take an epsilon positive. What is the meaning of saying that the distance between phi p and phi p prime is less than epsilon? We have already seen this earlier, right. That would mean that there exists some n such that the middle block of phi p and phi p prime should be the same. That means we can say that now at the finite stage, right, I can say that my p and p prime, they both belong to say v s minus 1 up to s minus n, right, this vertical triangle, this vertical rectangle, and I should say intersection with h s naught h s 1, say s minus n plus 1, or maybe I can take s minus n, does not matter. So, that means that my p and p prime, they both belong to the intersection of this vertical rectangle with this horizontal rectangle. What does that mean? So, let us go back to our figure once again, right. If we try to look into this figure once again, I have this vertical rectangle, which maybe I am claiming it as v s minus 1 s minus n, and maybe we have this horizontal rectangle, and I am claiming this to be my h s naught s 1 s minus s n. Now, that means now my p and p prime, they both belong to this region, this intersection of these two rectangles. And what happens to this rectangles if I see that the width of this happens to be lambda to the power n. So, if I am trying to look into what is this particular region, what is this particular width, right, we know that this particular width is lambda to the power n, and if I look into what happens to this particular width, right, we know that this particular width will be 1 upon mu to the power n. So, that means if I want to look into what could be the possible distance, because my p and p prime, they both belong over here. So, what could be the possible distance between p and p prime here? Since this is less than epsilon, means that this has to be, right, that means that at somewhere p and p, phi p and phi p prime, they agree on a middle part, right, which means that they belong to the same intersection, which means that the distance cannot be greater than, say, the distance between p and p prime. So, that would basically mean that mod of p minus p prime, right, it cannot be greater than, or maybe it is always less than 1 upon lambda to the power n plus, sorry, lambda to the power n, right, plus 1 upon mu to the power n. The distance cannot be greater than this, right. So, we can always choose a delta, right, such that a delta which is less than this part, right. So, that gives us that our mapping phi happens to be continuous, right. So, this map phi is continuous, and that gives me that phi happens to be a homomorphism. Now, since phi is a homomorphism, we have another, say, observation here, that my phi from lambda to sigma is a homomorphism. We have already observed that you have phi of f to be same as sigma of phi, right, at all points p of lambda. So, our phi is an homomorphism for which this relation holds, or in other words, I can say that if I take this diagram, this particular diagram commutes, right, which means that these systems lambda f and sigma sigma, right. These are topologically conjugate and what does that give? So, let me recall this once again. We knew something about our system sigma sigma. We have periodic orbits of all periods, we have uncountably many non-periodic points and we also have infinitely many points with dense orbit. So, what we can conclude is that, again I should write it in terms of the theorem here, right. We can conclude, what we conclude here is, for the system, that means for the horseshoe attractor, we have periodic orbits of all periods, uncountably many non-periodic points, and infinitely many points with dense orbits. So, the system, the horseshoe attractor has a very interesting kind of dynamics, but instead of looking into the horseshoe attractor, because again that is a very difficult system to study, what we have found out is the easier way to study is looking into the space of sequences, and we will come back to the space of sequences sometimes again later also. But right now we try to conclude this by one more observation. Now, we found an horseshoe. What was a horseshoe? Right? I can typically say that horseshoe was some kind of a compact set Q, right, such that I can write Q as a finite union of some other compact sets. So, let me say that Q can be written as a finite union of say Qi, say 1 to m for something. So, now I had Q written as finite union of Qi such that, what could you say about my Fq, right, when my Qi was such that, of course, my Qi intersection Qj was empty. So, these are pairwise disjoint, and what we can say about Q is again that Q is contained in, right, I am looking into the intersection of all I going from 1 to m f of Qi. What we observe is that whenever you have a system, right, which consists of or which contains a compact set Q such that Q can be written as a disjoint union of some finitely many compact sets which satisfy the property that Q is contained in the intersection of the image of each of this Qi, then we say that the system contains an M horseshoe. Now, this is what we mean by a topological horseshoe. So, then we say that the system contains an M horseshoe, and the existence of horseshoe in the system is good enough to tell me that the system is chaotic. So, we say that the system Xf is chaotic if it contains an M horseshoe for some m greater than equal to 2. Of course, we need equal to 2, 1 does not suffice here. So, for some m greater than equal to 2, if it contains it is called an M horseshoe. This particular construction, this particular Q is called an M horseshoe, and if it contains an M horseshoe, then we say that the system is chaotic. So, this is one more definition of chaos, and this is one more observation that such systems would be chaotic, but we are not going to get into details into horseshoe later. They do have their own looking practically, seeing whether there is a horseshoe or not is a very difficult exercise, but that gives us some kind of symbolic dynamics which occurs from this existence of M horseshoe, because M horseshoe will give you that the system can be splitted into a symbolic system, or basically you can have a sequence with M symbols, right, and again you have the same dynamics which gives you chaos. So, existence of a M horseshoe is enough to say that the system is chaotic, although realizing the chaos within is much easier when you get into the symbolic system. So, I think this is where we end today.